finding inverses is something you may have already done in a pre-calculus or previous course, but it's important to refresh that, or if it's the first time you've seen it, it's important to learn that. So if we have some function and we've guaranteed that it's invertible, so that's kind of step 0. What you have to do is, using the horizontal line test or a test for monotonicity or anything like that, you have to determine whether this is an invertible function. But once you've done that, the first thing you want to do is write y equals the function. So writing y equals f of x, that's kind of confusing. So I'm going to do it alongside this specific example. I'm going to say y equals x cubed. That's sort of step 1 here. The next thing you're going to do is you're going to swap the variables for x and y. You're going to rewrite it as x equals y cubed. And the reason you're going to do that is because now we're going to solve for y again. So if I want to get y by itself, what I need to do is I need to take the cube root. I need to say, okay, well that's the cube root of x is y. Or I could rewrite that as y equals cube root of x. Okay, well now that's my g of x function. So this is my candidate for my inverse. This is what I'm thinking, okay, this might be my inverse here. So now I need to verify that running this function through the original function gets me x. So that's step 1, 2, 3, 4. I need to say f, so something cubed. And what I'm cubing is the cube root of x. Well, that's like x to the 1/3 cubed. And if you remember how power to a power works, you multiply the powers. So you get x to the 1/3 times 3, which is x to the 1, which is x. Now you do the same thing. You say g of f. So you're taking something, you're taking the cube root of something. You're saying the cube root of, and that something is x cubed. So the cube root of x cubed definitionally is just x. So that's how we determine that. Now what we have to do is define the range of f as the domain of f inverse. Well, the x cubed, the range of x cubed is all real numbers. So the domain of this function is going to be all real numbers. And the domain of this function is all real numbers, so the range of this function is all real numbers. So in this particular case, it's just all real numbers all over the place. So finally, for step 5, you say f inverse of x is the cube root of x. Like that's all you're really doing. A lot of what you're getting at here is a verification step. This is really the point where you think you've identified. So you go from here to there. Or at least the last step of part 3, right? You might have to work, in this case you didn't really have to work through it, but you might have to work through it in step 3, and we're going to find that's true over here. So in this particular case, we're going to go through step 1, and that's going to be, we're going to write it as y equals x plus 1 over x. Which then I'm going to take another step and write that as x over x plus 1 over x, which is 1 plus 1 over x. That's how I'm going to write this, because I'm trying to save space for later. So in step 2, I'm going to say x equals 1 plus 1 over y. Okay? So all I've done is swap the variables. And the next step, I want to get y by itself. So I have to be a little more clever. So to do that, I need to get everything that doesn't have a y in it on the other side. So I need to subtract 1 from both sides to say x minus 1 equals 1 over y. So this is where it gets a little tricky. If you could do like a cross multiplication thing, but what you find is that if a equals b, then 1 over a equals 1 over b, as long as neither one of them is 0. So you have to be careful here. So you have to say, okay, well 1 over x minus 1 then is y. Because that would be like y over 1. So this is my candidate. This is what I think it is. Now, again, I have to be careful because I have to watch out for domain issues. if you went to the original function here, its function is not defined at 0. Can't be. And if you look at its range, if you look at like 1 plus 1 over x, if you look at that function, 1 plus 1 over x looks like something like that, and then down here, that's how that function works. And what you find is this function actually passes the horizontal line test on both of them because it never hits there, and it's strictly monotone in each of those intervals. So it's a little bit tricky there. But if we define this 1 over x minus 1 as my inverse function, I have to verify this in step 4. So that's my g of x. So f of g of x, so anywhere I see an x, I replace it with this thing. So I'm going to use this definition here. I'm going to say 1 plus 1 over x minus 1, right? That's g. So that's really just 1 plus x minus 1, which is x. Now for g of f of x, that's 1 over something minus 1. What I'm plugging in is this. 1 plus 1 over x minus 1, which is 1 plus 1 over x, which is x. So those two are satisfied. So I can say that f inverse of x is 1 over x minus 1. Now if you were to graph 1 over x minus 1, it looks a lot like this graph, but instead of it being, this is like 1 over x shifted 1 up. This is like 1 over x shifted 1 to the right. So you have something that looks kind of like this and that. Now it's not a perfect graph or whatever at all, but you have, in this case, these both have asymptotes at 0, and this is, and normally the vertical asymptote is 0 for 1 over x, but this is shifted over, so it has a vertical asymptote at x equals 1. So you have to be careful about your domains and ranges here, but ultimately it's really just watching out for where those vertical asymptotes are going to happen.